So now we're going to talk about current. Current is moving charges. So current is defined, so I'm going to use that 3 equal sign that I've used a couple of times before, as the amount of charge that passes a point in a certain amount of time. So it's kind of like velocity, but it's not velocity because it's number of charges, or the amount of charge that go by one point in a certain amount of time. So this is defined, the direction of current flow is defined as the motion of positive charges. And this was done because in the early things when they set up a battery and then they saw things happen like compasses move and eventually light bulbs light up and make electric motors go, they didn't know what was in the wires. In fact, one class I took in grad school, they decided to call it blueberry juice because we don't know what's going on in these wires. But we're just going to say that there's a current, and we use I for current, and no one knows why, we just do. But there's a current, and we are going to find that current flows from high potential to low potential, or positive to negative, because negative is obviously lower than positive. Now, we now know it's electrons. Electrons are negative. Electrons do not go from high potential to low potential. Electrons go from low potential to high potential. So the physical properties of what's happening in the wire are the exact opposite of this definition. But here's the nice thing, it doesn't actually matter. By defining conventional current, it's now sometimes called as the motion of positive charges, even though it's physically negative charges. Positive charges going to the right, negative charges going to the left, you have the same effect. So, units, you know that the unit of charge is the coulomb, you know that the unit of time is the second, so the unit of current is the ampere, often abbreviated amp, and the symbol we use is just the capital A. Ampere did a lot of studies on current electricity, hence the unit is named after him. So, that's first of 2 we're going to do today. The second is drift velocity, and this arises from the idea that, okay, there are electrons drifting through these wires, but the lights come on virtually instantaneously, so what's going on here? So if I draw a wire, or a portion of the wire, if I could actually see what's inside this wire, there are nuclei that do not move. They are locked in place. Each one, by the way, is surrounded by a cloud of electrons that stay with it. Only valence electrons in a conductor are free to move. And usually, only one from each atom. Because when one electron comes off this atom is now positively charged. So if there's a passing electron, it's not going to necessarily keep going. This might hold on to it pretty strongly. So taking a second one and a third one off just is not absorbed. It's energetically challenging. So again, remember, these are the nuclei with the protons buried in the nucleus, and their cloud of electrons. This is obviously not to scale because the nucleus should be really, really tiny down there if this is the size of the cloud of the electrons. And then we have a free electron. So let's just put it right here. Here's a free electron. Again, not to scale. We're going to apply an electric field here. So we're going to have a positive potential on this end, negative potential, of course, by connecting to a battery. That makes an electric field from positive to negative, that way. That makes current flow that way. But an electron's negative. Electrons don't want to go to the negative side. They want to go to the positive side. They go opposite the field. They go to higher potential. That's how they reduce their potential energy. So the electron wants to go this way, but there's all this other stuff in the way. So really what the electron does is bounce around randomly. But overall, this direction. So we call this VD, the drift speed, or the drift velocity. So even though the electron actually can be moving pretty fast in here, some numbers I just saw, this could be on the order of 1,000,000 meters per second, over very small spaces. But because of the electric field, it slowly, as it's bouncing around, moves this way. And we end up with numbers on the range of millimeters per second. Electrons do not zip through these wires. They bounce around and slowly go through these wires. Now, to get an expression for that, I'm going to do another picture. And this time I'm only going to draw electrons. So here's the wire, or just a portion of the wire. It has length L. It has cross-sectional area A. And I'm going to put lots of electrons in it. And overall, each of them is moving very slowly to the left, if it's like the other picture, with a velocity VD to the left, little tiny amount. Overall, really, all of these are bouncing around randomly like this, but overall drifting to the left. That's why we call it drift velocity. So first of all, how much charge is contained in this piece of wire? Oh, why are we doing that? Because current is charge over time. How much charge passes a point in a particular instant of time. So how much charge is in this volume? So the total charge in here is the number of electrons, which is really kind of hard to count. And so there's a new thing we're going to define. N is the number of charge carriers per unit volume. So the unit of this number is in our numerator. Per divide volume would be meters squared. So this gets at the idea that most of the time there's one electron donated or given up by each atom in the metal. So if we wanted to go farther than this, we could actually start from the actual mass density of this, use Avogadro's number, figure out how many atoms are in this volume, and then figure out how many charge carriers. But I'm going to give you this number, or this will be the purpose of the problem. So if N is the number of charge carriers per unit volume, then my total number of charges is that times the volume. Well, the volume of this cylinder, it's its length times area. So NLA. Now that's the number of charges, because number per unit volume, and then the volume. So then the charge on each, all of these are electrons, so I am going to use E. Remember, this is the elementary charge. E is 1.6 times 10 to the negative 19 coulombs. All electrons have the same amount of charge. And you would probably use absolute value here. We're talking about amount of charge because we've already been dealing with direction with the arrows. So that's how much charge is in this volume. But we want to find current. And current is the number of charges that pass this point in a certain amount of time. Well, as these exit, more are going to come in. And they're going to come in at a steady rate because they're all moving at this same drift velocity. So if we go way back to the beginning of the course, one way to measure that drift velocity is the length of this section divided by the time it takes these charges to pass through this volume. Because however much time it takes them to pass through this, well, then that's how many are going to leave and how many are going to come back in. So we can rearrange this. Delta T equals L over drift velocity. So now we can put them together. I is equal to, really should have deltas on here, delta Q over delta T. So NLAE over L over drift velocity. So the L's cancel, and I have a divided by drift velocity, so that comes up to the numerator. So I have my final answer. I equals NAEBD. So as you see when you do the problems, even for pretty significant currents, 30 amps. 30 amps is a lot. If 30 amps goes through you, you're dead. 30 amps is a lot, but you're going to get drift velocities that are very small, on the order of centimeters, millimeters, fractions of millimeters per second. Electrons are not zipping through these wires. So if we go back to the question, well, okay, if electrons are moving that slowly, then how do all the lights come on at the same time through the whole classroom? Because there are a lot of electrons. And essentially what happens is this electron coming in pushes this one, repels this one, repels this one, repels this one with that extra push. And that push travels at the speed of light. It's the same idea as when you have heavy traffic on the highway. You have a lot of cars passing through that highway, even though they're all moving very, very slowly because there's so many cars. Another analogy for this is pretend this is your hose full of water out in your backyard. When you turn it on at one end, you see water come out pretty quickly out the other end, especially if it's been on recently. Because if it's full of water, turning it on at one end, the pressure wave kicks it out pretty fast out the other end. So the electric field is set up very quickly because of those electrons pushing against each other. It's not instantaneous. It does have to travel at the speed of light in the material, but that is so fast that to our perception, it's about the same. So that's it for video number 1 for current electricity.